Hi guys, this is Mrs. Whoops, I ran into the camera, sorry. Hi guys, this is Mrs. Gastler, and in this video we are going to derive the equation for centripetal acceleration, and then we're going to pair it with Newton's second law for an object moving in uniform circular motion. Okay, so this goes with uniform circular motion, which we talked about in another video. All right, so circle. Object going in a circle. Let's say it starts at point A. Our goal here is to get an equation that says the centripetal acceleration equals something, okay? And what we know is that acceleration is the change in velocity over the change in time. And when we have an object going in a circle, its velocity is changing, except its direction is changing and not its speed. So what do we do with that? So the direction is constant, but the speed, whoops, just kidding, hang on. I actually can erase that. The direction is changing, but the speed is constant. That's what I meant to write. So what do we do with that? That's what we're trying to find out. So let's say our object starts at A and it has some radius, okay? And let's say it's going this way, so this represents its initial velocity. And it's a vector, so it has a little vector symbol on it. And after some time, it's at point B. And at point B, now it's going this way, but it's still the same velocity. So let me try and draw those arrows exactly the same length, right? And now that's the final velocity, okay? Now the r is the same, but it has traveled through some angle, right? Some angle has passed that it's gone. And so my goal, what I want to do using this right here is using some geometry again. There's lots of geometry in uniform circular motion. I want to use some geometry to see if I can't come up with a change in velocity. So what I'm going to do is I'm going to take these two angles here and I'm going to make a triangle right over here out of them. So here's my VI and here's my VF. And you're just going to take my word for it. I drew those exactly the same as those. Can you see? Yeah, I know you can. Okay. Now, when I'm adding vectors or subtracting vectors, or I'm looking for the change of velocity, I can use parallelogram methods, which I don't know if you remember that, but you can draw VI plus VF would look like this, drawing them end to end like that. But if I'm going to subtract them, what I would do is I would draw them like this. So VI minus VF would actually point in the other direction, so I would point it like that. And so this vector right here is actually the change in velocity. Okay, so going this way across the parallelogram would be plus, and going this way across would be minus, which now I just muddled that up and you can't tell, but this V, delta V is VF minus VI, okay? So this little arrow right here represents delta V, okay? Now, since this pen is running out of ink here. Let me try a different one. Go with this one. I think it was working pretty well. Since VF, the magnitude, is the same as VI, which is just V, I'm going to replace that in my triangle. So this triangle is going to look like this. Oops. Pretend this is exactly the same size. Delta V. And I'm not sure if you can tell, but since I rotated it this way, these arrows are going to rotate the same amount of an angle too. So this angle right here is the same. Okay, and so I have this. And so I'm going to bring over this triangle here too that has my R's on it. So I have R and R. Because the radius of the circle didn't change. It's uniform circular motion, so the R is going to stay the same. So this right here is the angle. And this right here, just like this was delta V, this is delta R. And so I have some similar triangles right here. Here, let's try, we'll label my steps here. And I drew this out of there. And so since those are similar triangles, I can write some things. And so I can write some relationships. So since these are similar triangles, delta r over r is the same as delta v over v. And that is going to allow me to get an expression for delta v. So I'm just going to multiply v over to the other side. So v delta r over r. Okay. And so this is something that I'm going to plug in up there. So I'm going to have AC equals delta V over delta T. And I'm going to plug in this for delta V. So I'm going to have V delta R over R delta T. And I don't know if you can see it. Let me circle it for you with this pencil right here. That right there. Delta R, that's how far it went. And delta t is an amount of time. And so that's actually how fast it's going. So this becomes v times v over r, which is v squared over r. Isn't that magical? Okay, maybe you don't think it's magical. I think it's magical. So what I was looking for, an expression for the centripetal acceleration, is v squared over r. Right there. Okay, so this relates the linear speed of an object going around a circular path to the radius of the circle and the centripetal acceleration that the object is feeling. So remember that centripetal acceleration is directed along the radius. Okay, so what do I do if I'm looking for the centripetal force? All right, so we'll deal with more complicated problems later on, like what if I'm in a vertical circle? But right now we're just gonna talk about objects that are in horizontal circles. So the only force, the net force that's going to be acting on it is going to be the centripetal force toward the center of the circle. So if the net force is that central force, I can just leave it like that. Then MA becomes MAC. Okay, so the central force becomes mv squared over r. And so this can be used to solve the problems. And then you just have to remember that this central force, the question is, what is supplying the central force? Is it friction? Is it normal? Is it gravity? Is it tension? What's supplying the central force? Once you know that, and you know enough pieces of information, you can use this formula or some combination of formulas to be able to solve problems about objects going in circles. And that is all I have for you. Thanks for watching. Can you see all that? Yeah, okay.